Have you ever stopped to truly marvel at the brilliant colors of fireworks or, that distinct, almost otherworldly glow of a neon sign? What you might not realize is that these everyday things, when scientists really looked closely, well, they pose these deep mysteries. Mysteries that actually shattered our fundamental understanding of matter and energy. This wasn't just a small adjustment, it was a full-on revolution that fundamentally changed how we view the atom itself.
It's fascinating, isn't it, how those seemingly simple observations, like how light heats up a metal surface, or the very specific colors that a gas gives off, how they force physicists to completely abandon classical physics. They had to embrace something, well, entirely new.
Right. For centuries, energy was just waves and matter was just particles.
Exactly.
Yeah.
Purely wave-like, purely particle-like. This deep dive today, it's about that journey, the shift to realizing their intertwined dual nature. Quite astonishing, really.
Right.
Our mission today is to give you a clear step-by-step guide through these groundbreaking ideas, the laws, the examples, all from Silberberg and Amits's chemistry. The molecular nature of matter and change, Chapter 7. Think of it as a shortcut to getting up to speed on the quantum mechanical model of the atom. And we'll do it all just by talking it through, no visuals needed.
Okay, so let's start with light itself. For a long time, yeah, we understood light purely as a wave, like ripples spreading across a pond.
Electromagnetic radiation.
Right, traveling at the speed of light, and characteristics like wavelength and frequency, they're inversely related, right? That determines its energy.
Precisely. And classically, that wave model worked beautifully for everyday stuff, like why a magnifying glass works or how rainbows form through refraction light bending as it goes from air to water, making a straw look bent.
Or diffraction waves bending around things and interference patterns.
Yeah, all perfectly explained by waves. But that neat classical picture, it just hit a wall when scientists started looking really, really small at the atomic scale.
Okay, so what were those first cracks? Where did the classical understanding start to fail?
Well, there were a few key observations that just didn't fit. They forced a radical reevaluation.
And here's where it gets really interesting, right? Two critical observations especially made scientists think, hang on, maybe light isn't just a wave. The first was something called blackbody radiation.
Ah, yes. You heat up a solid object, it glows. It emits electromagnetic radiation.
Like a blacksmith's forged metal getting red hot, then orange, then white hot as it gets hotter.
Exactly. But classical physics just couldn't explain the relationship they observed between the energy being emitted and the wavelength, the color of the light at different temperatures.
Yeah.
It just didn't match the predictions.
So how did Max Planck tackle this puzzle?
Well, in 1900, Max Planck, in what he later called an act of despair, came up with this revolutionary idea. He proposed that the object couldn't just emit or absorb any amount of energy. It could only do so in certain discrete quantities. He said energy is quantized.
Quantized, like steps.
Exactly like steps. Imagine energy isn't a smooth ramp you can slide up and down continuously. It's a staircase. You can only be on step 1 or step 2 or step 3, nowhere in between. Planck said atoms behave like this. Their energy exists in these fixed amounts.
Okay, and each fixed amount is called?
A quantum. And the energy of one quantum is equal to high, where h is a fundamental constant, now called Planck's constant, and is the frequency of the light. This single idea that energy itself comes in packets, it just shattered classical physics. That laid the groundwork for, well, everything that followed in quantum theory.
Wow. That is a profound shift. And then came the photoelectric effect, which gave even more sort of compelling evidence for light acting like a particle. What was so confusing about that one?
Right, the photoelectric effect. When light shines on a metal surface, under the right conditions, a current slows. That means electrons are being ejected from the metal.
Okay, seems simple enough.
But there were two features that classical wave theory just couldn't explain. First, there's a threshold frequency. You needed light of a certain minimum frequency, a specific color or higher, to eject electrons. Below that frequency, nothing happened, no matter how bright the light was.
Which is weird. Classically, you'd think brighter light, more energy should always work eventually.
Exactly. Classical theory predicted any color should work if the light was intense enough. And the second puzzle was the absence of a time lag. If the light's frequency was above the threshold, electrons were ejected immediately, even if the light was really dim. Classical theory predicted a delay for dim light, like the electrons needed time to save up enough energy from the wave.
So, no saving up and a minimum energy requirement per electron. What was the solution?
Enter Albert Einstein in 1905. Building on Planck's quantum idea, he proposed that light itself isn't a continuous wave, but is actually particulate. It's made of these tiny bundles or packets of energy,
Packets, he called them.
photons. And the energy of each photon is given by Planck's formula, E equals high.
Ah, so the energy is tied to the frequency, not the brightness.
Precisely. Einstein realized that the intensity or brightness of the light is about the number of photons hitting the surface per second, not the energy carried by each individual photon. Think of it like trying to knock a book off a shelf. You could throw 1,000 ping pong balls at it, lots of impacts, low energy each, and nothing happens.
Right.
But one baseball, just one projectile, but with enough energy, knocks it right off.
Got it. So an electron needs to get hit by one photon that has enough energy, meaning high enough frequency, to break free from the metal.
Exactly. That perfectly explains the threshold frequency, the minimum energy needed per photon. And it explains the immediate ejection one photon hits. One electron comes out, no waiting, no saving up.
So light acts as both a wave and a particle. Yeah, mind-blowing. Okay, so how did this radical new understanding of light apply to atoms themselves and the light they emit?
Well, that brings us to atomic spectra. This was another major puzzle. See, if you take white light and pass it through a prism, you get a continuous spectrum, a smooth rainbow of all colors.
Right, like sunlight.
But if you take a gas of a specific element, say hydrogen or neon, and you excite it with electricity, like in a neon sign, and then pass its light through a prism, you don't get a rainbow. You get a line spectrum,
Meaning?
a series of distinct, sharp lines of color at very specific wavelengths, separated by black spaces. It's like a barcode for the element. You mentioned neon signs, that brilliant orange-red glow. That's neon's unique line spectrum. Every element has its own characteristic fingerprint of spectral lines.
Okay, but why was this a problem for classical physics and for Rutherford's model of the atom, the one with the nucleus and electrons orbiting?
Two big problems. First, classical physics predicted that an electron orbiting a positive nucleus should continuously emit radiation, lose energy, and spiral into the nucleus. Atoms should collapse, which clearly they don't. Second, that continuous radiation should produce a continuous spectrum, like a rainbow, not these sharp, discrete lines. Rutherford's model, based on classical ideas, just couldn't explain stability or line spectra.
So the atom was unstable according to the old rules, and the light it emitted was a complete mystery. How did Niels Bohr step in to try and fix this?
In 1913, Niels Bohr, who was working with Rutherford, proposed a new model specifically for the hydrogen atom, and he boldly incorporated Planck's and Einstein's quantum ideas. His model had a few key postulates, really revolutionary ones.
Okay, what were they?
First, he said the hydrogen atom has only certain allowed energy levels for its electron. He called these stationary states. Think of them as specific fixed orbits, though we now know that's not quite right. Higher energy levels meant orbits farther from the nucleus.
Stationary state. So the electron doesn't radiate energy when it's in one.
Exactly. That was his second postulate. The atom does not radiate energy while in one of its stationary states. This directly contradicted classical physics, but it was necessary to explain stability.
Okay. So how does it change states?
That's the third postulate. The atom changes from one stationary state to another only by absorbing or emitting a photon. And the energy of that photon must be exactly equal to the difference in energy between the two states.
Ah, back to the quantum staircase idea.
Precisely. An electron can jump up a step by absorbing a photon of the right energy, or drop down a step by emitting a photon of the right energy. It cannot exist between the steps.
And each jump corresponds to a specific energy difference, therefore a specific photon frequency or wavelength.
Which translates directly to a specific line in the spectrum. Since an atom only has these specific quantized energy levels, only certain discrete amounts of energy can be absorbed or emitted as photons. This beautifully explained why atomic spectra consist of distinct lines rather than a continuous rainbow. Different series of lines, some in the UV, some visible, some infrared, correspond to electrons dropping down to different final energy levels, different steps on the staircase.
That's brilliant. Bohr's model really was a monumental leap. It showed atomic energy is quantized.
It absolutely was.
Uh-huh.
But it wasn't the final answer.
Right, you mentioned limitations. What were they?
Well, the biggest one was that it only really worked perfectly for hydrogen, which has just one electron. As soon as you try to apply it to atoms with more than one electron, the calculations failed. The model couldn't handle the complex interactions, the repulsions between multiple electrons.
And there was a more fundamental issue, too.
Yes. We eventually learned that electrons don't actually move in fixed, defined circular orbits like planets. Bohr's picture was too simplistic in that sense. However, That core idea that an atom's energy exists in discrete quantized levels, a ground state and various excited states, that remains absolutely central to our modern understanding.
And even though the model was limited, the phenomenon it explained, these unique atomic fingerprints, has become incredibly useful, right?
Hugely useful. Spectrometry, the analysis of these spectra, is a cornerstone of chemical analysis. You have emission spectra, like in flame tests, or identifying elements in fireworks by their colors. Strontium makes red, copper makes green.
And absorption spectra.
That's where you shine light through a substance and see which wavelengths get absorbed. It's how we know chlorophyll absorbs red and blue light, which is why leaves look green. They reflect the green light. Astronomers use both emission and absorption spectroscopy constantly to figure out what stars, planets, and distant galaxies are made of. It's amazing what we can tell from light.
Okay, so we've got light acting as both wave and particle. Bohr used that particle nature photons to explain atomic spectra, even if his orbits weren't quite right. But that raises another, maybe even deeper question. If light waves can act like particles, what about matter? Could particles, like electrons, act like waves?
Exactly the question Louis de Broglie asked in the 1920s. He was inspired, partly, by Einstein's E equals mc/I, which had already shown this deep connection, this equivalence between matter and energy.
Matter and energy are two forms of the same thing.
Right. So de Broglie thought, well, if energy, like light, can have particle-like properties, maybe matter, like electrons, can have wave-like properties.
Right.
He had this analogy. Maybe electrons confined in atoms, in those Bohr energy levels, behave like vibrating guitar strings.
Oh, so.
A guitar string, when plucked, can only vibrate at certain frequencies, producing specific notes. It forms standing waves with fixed wavelengths. De Broglie proposed that maybe electrons could only exist in orbits where their associated wave fit perfectly, creating a standing wave. He even derived an equation for the wavelength of a particle. The de Broglie wavelength, where h is Planck's constant, m is mass, and u is velocity.
Okay, wait. Everything has a wavelength. A baseball. Me.
According to the equation, yes. But here's the crucial part. For everyday objects, macroscopic objects like a baseball, the mass m is relatively large. This makes the calculated de Broglie wavelength incredibly tiny, many orders of magnitude smaller than the object itself, completely undetectable, practically meaningless.
But for an electron.
An electron has a tiny mass, so even if it's moving fast, its de Broglie wavelength can be significant, maybe around 10 meters, which is actually comparable to the size of atoms themselves.
Whoa, so it's a real, potentially measurable effect for electrons. Was there experimental proof?
There was, and quite quickly. In 1927, two American physicists, Davison and Germer, performed a landmark experiment. They showed that a beam of electrons, when shot at a nickel crystal, exhibited diffraction.
Diffraction, that's a wave behavior, right? Like light bending around an obstacle.
Exactly. X-rays, which are waves, were known to diffract off crystals. Davison and Germer showed electrons did the same thing. It was direct, undeniable experimental proof of the wave nature of electrons.
That must have been huge. Did it lead to anything practical?
Absolutely.
Oh.
It led directly to the invention of the electron microscope. Because high-speed electrons have wavelengths much shorter than visible light, they can be used to resolve much finer details. Electron microscopes give us incredible magnification, visualizing tiny biological structures, material surfaces, things far too small for light microscopes, up to 200,000 times magnification or even more.
Amazing. So electrons are waves, but we also know they're particles, they have mass, charge.
And just to complete the symmetry, Arthur Compton, around 1923, provided strong evidence for the particle nature of photons through the Compton effect. He shot X-ray photons at graphite, which contains electrons. He observed that the scattered X-rays had a longer wavelength, meaning they had lost energy.
Where did the energy go?
It was transferred to the electrons, along with momentum. The collision behaved exactly like two billiard balls colliding. The photon knocked the electron, transferring energy and momentum. This showed that photons, these packets of light energy, also carry momentum like particles do.
So it goes both ways. Light has particle properties, photons, and particles, electrons, have wave properties.
Precisely. This is the principle of wave-particle duality. The neat classical distinction between matter, chunks, particles, and energy, diffuse waves, completely breaks down at the atomic scale. Both matter and energy exhibit both wave and particle characteristics. They possess two faces, and which one we observe simply depends on the type of experiment we perform. It's not a contradiction or a flaw. It's just the fundamental nature of quantum reality.
Wow. Okay, that is truly profound. But it leads to another problem, doesn't it? If an electron is both a wave and a particle, Can we ever really know exactly where it is and what it's doing? Like, track its path precisely?
And that's where Werner Heisenberg comes in. In 1927, he formulated his famous uncertainty principle.
The one that says you can't know everything at once.
Basically, yes. More precisely, it states that it is fundamentally impossible to simultaneously know both the exact position and the exact momentum, which includes velocity, of a particle with perfect accuracy.
This is trade-off.
An inherent trade-off, described by the equation H-4. If you design an experiment to measure the position very accurately, making L's very small, your measurement inherently disturbs the particle's momentum, making your knowledge of its velocity less accurate, making large, and vice versa. You can know one well, but only at the expense of the other.
So what does this actually mean for an electron buzzing around inside an atom?
Well, for a big object like a baseball, Planck's constant h is so incredibly small that these uncertainties are completely negligible. We can still predict its trajectory perfectly well for all practical purposes, but for an electron, because its mass m is so tiny, the uncertainty becomes significant. If you try to pinpoint an electron's position within an atom, the uncertainty in its velocity becomes huge. In fact, the calculation shows the uncertainty in its position can be about 10 times larger than the diameter of the entire atom itself.
10 times. So we basically have no precise idea where the electron is inside the atom at any given instant.
Exactly. We cannot know its exact location and its exact path or trajectory. The uncertainty principle fundamentally limits our ability to do that. It means Bohr's neat planet-like orbits just aren't physically possible or meaningful.
So if we can't have definite orbits, what do we have? How do we describe the electron in the atom now?
This is where we finally arrive at the modern view, the quantum mechanical model of the atom. With wave-particle duality and uncertainty firmly established, Bohr's model, despite its insights, had to be replaced. We needed a completely new mathematical framework.
And that framework came from?
Primarily from Erwin Schrödinger in 1926. He developed a complex mathematical equation, the Schrödinger equation, that treats the electron explicitly as a matter wave. The solutions to this equation are mathematical functions called wave functions, usually represented by the Greek letter psi.
Okay, a wave function. What does that tell us?
Well, the wave function itself describes the electron's matter wave in 3 dimensions, but it doesn't directly represent a physical path or location. A specific solution to the Schrödinger equation, corresponding to a particular energy state and wave function, is called an atomic orbital.
Right, you hear orbital a lot. So crucially, what's the difference between Bohr's orbit and this quantum orbital?
Big difference. An orbit, in Bohr's sense, was thought of as the electron's actual defined path, like a planet's orbit. An orbital, in the quantum model, is a mathematical function that describes the electron's wave-like properties and its energy state. It does not describe a definite path.
So if the orbital isn't a path, and the uncertainty principle says we can't know the exact location, how do we talk about where the electron is?
We talk about probability. While the wave function itself isn't directly physical, its square spot does have a crucial physical meaning. It's called probability density. At any given point in space represents the probability of finding the electron within a tiny volume around that point.
Ah, so it's not where it is, but where it's likely to be found.
Exactly. We can visualize this probability. Sometimes it's shown as an electron density diagram or electron cloud. Imagine taking thousands of snapshots of the electron's position over time where the dots are densest. The probability of finding the electron is highest. It's like a long exposure photo of a firefly buzzing in a dark room. You don't see its path, just a blurry cloud showing where it probably spent its time.
Okay, that helps visualize it. Are there other ways?
Yes, another useful tool is a radial probability distribution plot. This plots the total probability of finding the electron at a certain distance from the nucleus, summing up the probabilities in a thin spherical shell at that distance. Interestingly, while the probability density is highest right at the nucleus for some orbitals, the radial probability often peaks a little distance away from the nucleus.
Why is that?
Think about collecting fallen apples around a tree. The density apples might be highest right near the trunk, but if you count the total number of apples in foot-wide circular rings moving outwards, the ring a little distance away will likely have the most apples, just because the area of the ring is larger. Same idea with the electron shell volume. So the electron is most likely found near, but not exactly at, the nucleus.
And how do we define the size of this probability cloud, the atom's edge?
Since the probability technically extends out forever, we usually define a boundary surface. a probability contour that encloses a certain percentage of the total electron probability. A common choice is the 90% probability contour of the volume where the electron is found 90% of the time. That gives us a practical picture of the orbital's size and shape.
Okay, this probabilistic picture is much more complex than orbits. How do we actually distinguish between different orbitals, different electron states?
We use a set of 3 quantum numbers that arise naturally from solving the Schrödinger equation. These numbers essentially give each orbital its unique address and specify its key properties:
Yep.
energy, shape, and orientation.
Okay, let's break them down. What's the first one?
The first is the principal quantum number, denoted by n. This is a positive integer. N equals 1, 2, 3, and so on. N is the primary indicator of the orbital's size and energy level. Higher n means a larger orbital, generally farther from the nucleus, and a higher energy. This directly corresponds to Bohr's energy levels or shells.
Okay, so N is like the main energy level or shell. What's next?
The second is the angular momentum quantum number, denoted by L. Its possible values are integers ranging from 0 up to n1. So the value of n limits the possible values of L, primarily determines the shape of the orbital.
So N sets the level and L defines the shapes possible within that level. Like if N1L can only be 0, if N02L can be 0 or 1.
Precisely. It creates this hierarchy of possibilities. And the third number
The third one.
is the magnetic quantum number, denoted by ML. Its possible values are integers ranging from LL through 0 up to plus L. So the value of L limits the possible values of ML, determines the orientation of the orbital in three-dimensional space.
Okay, so NL and ML together specify a unique orbital. How does this relate to the terms sublevel or subshell?
Good question. An energy level or shell is defined just by the n value. Within a given level n, all orbitals with the same L value belong to the same sublevel or subshell. And we actually use letters to designate the L values, the sublevels. L is called an S sublevel, L1 is called a P sublevel, LN2 is called a D sublevel, LL3 is called an F sublevel. It continues alphabetically after F, but S, P, D, F are the most common.
So if NP2 and L is 0, that's the 2's sublevel.
Exactly, and if N3 and L1, that's the 3P sublevel.
And how many orbitals are in each sublevel?
That's determined by the number of possible L values for a given L. Since LO goes from L to plus L, including 0, there are 2L plus 1 possible values. So for an S sublevel, L0, 2, 0 plus 1 equals 1. There's only one S orbital in any S sublevel. Its only L value is 0. For a P sublevel, L1, 2, 1 plus 1 equals 3. There are 3 P orbitals in any P sublevel, corresponding to LL. There are 1, 0 plus 1. For a D sublevel, L2 plus 1. There are 5 D orbitals, and for an S sublevel, LD2, 3 plus 1 equals 7. There are 7 F orbitals.
Okay, that makes sense. It's a very structured system. Now, the shapes. You said all determines the shape. Can you describe them without pictures?
Let's try. S orbitals, where L0 are always spherical. The electron cloud is perfectly round, centered on the nucleus. The 1's orbital is the smallest sphere. The 2's orbital is a larger sphere, but it actually has a node, the spherical surface inside, where the probability of finding the electron is 0. Think of it like an expanding onion with layers of probability getting bigger with n.
Okay, sphere for what about p orbitals?
P orbitals, where L1, have a dumbbell shape. Imagine 2 lobes of electron density on opposite sides of the nucleus, with the nucleus itself lying on a flat plane, a nodal plane, where there's 0 probability. Since there are 3 possible ML values for L1, there are 3 P orbitals, and they are oriented perpendicular to each other, typically along the X, Y, and Z axes. Think of 3 identical 2-lobed balloons tied together at the center, the nucleus, each pointing along a different axis. The first possible P orbitals appear when n equals 2, the 2 P orbitals. 3 perpendicular dumbbells. Yeah, got it. And D orbitals, those sound complicated. D orbitals L2 are definitely more complex. There are 5 of them. 4 of the 5 have a characteristic 4-lobed cloverleaf shape. Imagine 2 perpendicular dumbbells intersecting at the nucleus. These 4 cloverleaves lie in different planes, xi, xa, yz, or between the axes. The 5th orbital, often called the D mirror, looks different. It has 2 main lobes along the z-axis, like a orbital, but also a donut or torus of electron density in the DC plane around the middle. They first appear when Na3, the 3rd orbitals.
4 clover leaves and a dumbbell with a donut.
Okay.
And F orbitals.
F orbitals, L3. All 7 of them are even more intricate, with multiple lobes and nodes. Their shapes are quite complex to describe simply in words. They first appear when N is 4, the 4 F orbitals.
Wow, it gets complex fast. Is there anything special about the energy levels in hydrogen compared to other atoms?
Yes, a very important point. For the hydrogen atom, because it only has 1 electron, there are no electron repulsions to worry about. In hydrogen, the energy of an orbital depends only on the principal quantum number, n. This means that all orbitals within the same shell, same n, have the same energy. So the 2s orbital and the 3 2p orbitals all have identical energy in hydrogen. They're called degenerate. However, for all other atoms, multi-electron atoms, the situation is different. Due to electron repulsions and shielding effects, the energy of an orbital depends on both n and l. Within a given shell n, the s sublevel is lowest in energy, then p, then d, then f. So 2s is lower energy than 2p in, say, a carbon atom. This energy difference is crucial for understanding electron configurations, which we'll get into later.
Ooh, okay, what a journey. We started with, just looking at glowing streetlights and fireworks and ended up deep inside the probabilistic cloud of an electron. We've really unpacked how our whole view of matter and energy had to fundamentally change, leading us to this incredible, if strange, quantum mechanical model of the atom.
Indeed. It's quite a story. From those first puzzles with light black-body radiation, the photoelectric effect, through the groundbreaking ideas of Planck and Einstein, realizing energy is quantized into photons. Then Bohr's model, a huge step with its quantized energy levels explaining spectra, but ultimately limited because electrons aren't in simple orbits, which forced us to embrace the even weirder ideas of wave-particle duality for everything and Heisenberg's uncertainty principle limiting what we can even know.
Right, and all of that built the foundation for Schrödinger's equation and this modern model, where we don't have orbits, we have orbitals, these mathematical descriptions of probability clouds, defined by quantum numbers n, l, and ml with specific shapes and orientations.
Exactly. It replaces certainty with probability. We describe where electrons probably are based on their wave functions rather than where they definitely are along some path.
So what does this all mean for us trying to understand chemistry? It means the atom isn't like a tiny solar system at all. It's more like a dance of probabilities governed by these strange quantum rules and described by elegant mathematics. These rules are totally counterintuitive compared to our everyday world, but they are absolutely essential. They explain chemical bonding, reactivity, how lasers work, how semiconductors function, basically everything modern chemistry and technology relies on.
It's true. So maybe next time you look at a sparkler fizzing away, or even just the screen of your phone emitting light, take a moment. Consider the absolute revolution in thinking Planck, Einstein, Bohr, de Broglie, Heisenberg, Schrödinger that had to happen for us to even begin to understand how that light is produced at the atomic level. It really reminds us that sometimes the biggest breakthroughs come from questioning what seems most obvious, from challenging centuries of classical thought, and being willing to embrace the utterly unexpected.
A great point. It makes you wonder, what other obvious truths about our world might just be waiting for the next quantum-style revolution to overturn them?
A provocative thought indeed. We hope this deep dive into quantum theory and atomic structure has maybe sparked some new questions for you and encourages you to keep exploring this fascinating fundamental area of science.